Hello. We've been talking about resonance, and so resonance is all about stability, as we learned, and so now we know something about how organic compounds can be stable when we think about pi bonds, when we think about lone pairs, even when we think about carbocations or other formal charge, right? We know where charge is stable, we know where carbocations. How can we stabilize carbocations? We can make resonance structures of them, right? How do we stabilize pi bonds and lone pairs? We can convert them into other pi bonds and lone pairs and distribute that charge throughout the molecule. So we've talked about stability of all of those things, and those are the things that we kind of, when we started, we said where are electrons in organic molecules, and that's important, right? And when we started, we said there's four places, right? There's pi bonds, lone pairs, carbocations. Those three we've already talked about, and there's sigma bonds. So today, in this video, we're going to talk about the stability when we have only sigma bonds to worry about. Okay, and that's called conformational isomers because sigma bonds allow things to rotate, and so depending on how far they rotate and what things they rotate into alignment with other things, um, that will determine the stability of this. So we'll draw some structures, we'll look at some conformations, and then we'll call it a video. Okay, so conformational isomers. Right, so let's pick a molecule that's got lots of sigma bonds and doesn't have any pi bonds or lone pairs, so we can make this very simple. Let's do pentane. Okay. All right, very simple. We got pentane, we got nothing but carbons and hydrogens, we got nothing but sigma bonds. Let's look at these two carbons right here. I'm going to call this carbon A. This would be carbon 2, or whatever, and then behind it is carbon B. Right? And so if we look at carbon A has a CH3 group attached to it on one side. It has this 3-carbon chain attached to it on the other. And what we're not seeing is we're seeing there's 2 hydrogen bonds. There's 1 hydrogen here. There's 1 hydrogen here. Okay. And so, all right, so when I draw it this way, what this means is that when I have a wedged bond or a bolded bond like that, a wedged bond means it's coming out of the screen at you. Coming out at you. Right? So imagine it's like pointed directly out of the screen, right? And then the dashed bond is, of course, the opposite. Away from you. Okay, so this is one of those things that students always get confused about because the way we draw them, we have the wedge going a little bit to the right and the dash going a little bit to the left. And what if we switch those things and all that? It doesn't actually matter because when you look at organic molecule, the way it is, so if this is our organic molecule, right, where the carbons are going kind of up and then down, going this way, right? The hydrogens are going like this, and they're pointed pretty much directly. One is right at you, and one is right behind you. But of course, if we draw it this way, you wouldn't, there we go. You wouldn't be able to see the hydrogens because they'd be overlapping each other. So instead, we draw them slightly off like this. But in reality, if you draw them like this, where the wedge is on this side and then the dash is on the other side, or if you draw them like this, where it's the other way around, the wedge is on this side and the dash is back here, same thing, right? Because really what it is they're aligned exactly. So when you draw this, don't worry about, oh, is my wedge or the dash in the right place? You can switch them and it doesn't really matter. Okay, so now where's my, all right. So what's happening here is that all the electrons, stop it, all the electrons in this molecule are in sigma bonds. Right? And so what happens is these electrons that are in these sigma bonds start to repel each other. And so instead of being just all kind of attached to each other, or they try to get as far away from each other as possible. All the electrons are in sigma bonds and they repel each other. Right? And so this carbon A is in this tetrahedral shape. So carbon A, any sp3 carbon, sp3 carbons like carbon A has a tetrahedral shape. And this is true of any carbon that is only sigma bonds, right? All the sigma bond, any carbon that has 4 sigma bonds to it is always going to be in this tetrahedral shape. It's always going to have kind of two, losing my place here. It's always going to have 2 straight line bonds that are kind of one going to the left and one going to the right. It's going to have a wedge that's coming out at you, and it's going to have a dash that's going back. So we could do the same thing on carbon B. We could do the same thing over here on carbon, I guess this would be carbon C at this point, right? Even these carbons at the end, right, are going to have a wedge, a dash, and then they're going to have another straight line, and that's going to be the other H, right? So all of these carbons are tetrahedral, and the reason they're tetrahedral is because these electrons repel each other. Now I want to pull out just carbon A and carbon B and draw them a little bit differently. So carbon A, right? Carbon A has, if we look at it kind of in this direction, so I'm going to look down this bond right here so that carbon B is behind carbon A. So here's carbon A right here, right? Carbon B is behind carbon A, so it's kind of going behind it there. We have a methyl group that's kind of coming right at us. And we have 2 hydrogens, one in front of us, one behind us. Carbon B is going to look very similar, except that carbon B is going to have, behind it is going to be the 2 other carbons that are part of the chain. In front of it is going to be carbon A and 2 hydrogens. Okay. And so what's interesting is when we look at this, of course, carbon A and carbon B are connected to each other, right? Here's carbon B attached to carbon A, here's carbon A attached to carbon B. And so if we look at these two in this way, and we kind of put them together and just kind of, we're going to plop carbon A right on top of carbon B. So I'm going to put carbon A right here, and I'm going to put carbon B behind it, right? So carbon A is the dot, carbon B is the circle. Right? And then we look at what are the things that are attached here. Attached to carbon A, we have a CH3 group, and then we have hydrogens here and here, hydrogen, hydrogen. And if we look at carbon B, attached to carbon B, we have the CH2, CH3, and then we have a hydrogen, and we have a hydrogen, right? And again, these angles are offset a little bit so that we can see what they are, but really they're kind of aligned the same way. And so what we know is that when electrons are in sigma bonds, they repel each other. And what we're going to see is that if we line these up like this, where all the groups on the front carbon overlap exactly with the back carbon. So groups on the front carbon overlap with groups on the back carbon. This is called an eclipsed conformation. Oh my gosh, I'm running out of space. Eclipsed conformation, right? It's like an eclipse. When the sun passes, or when the moon passes in front of the sun, that's an eclipse. Carbon A in this case is the moon. Carbon B is the sun. It's passing in front and it's blocking, it's reacting with those. So what happens in an eclipsed conformation is that this repulsion of these electrons, the electrons in this bond right here, and the electrons in this bond right here, are going to repel each other. They're going to push each other apart, right? And so in the eclipse conformation, we say, what am I going to say this? I guess we'll write it down here. Eclipsed conformations are unstable because of electron repulsion in the sigma bonds. Okay, and this has a very special name. Instead of saying electron or electron repulsion in sigma bonds, we call this steric repulsion. Right, so this steric repulsion is, oh man, I'm not going to be able to underline all this, am I? Nope. Is due to all of this electron-electron repulsion in sigma bonds. right? So that's basically the setup for, oh no, I've lost my mouse. There it is. So that's the setup for steric repulsion for conformational isomers, right? We've seen one conformation is eclipse conformations where everything lines up exactly more or less right up with each other. And what happens is the electrons in this bond, my right hand is a bond, my left hand is a bond, the electrons in these two kind of push each other apart. And what we're going to see in the next video is that they push each other until they get as far away from each other as they can. So between now and when you watch the next video, think about what happens if we push all those groups so that they're as far apart from each other as possible. And you'll see the answer when you click on the next video.